This next problem involves two special triangles. So you can see that we have a 60-degree angle in here, 90, so this must be 30. So this is a 60-30 triangle. And again, it's good to visually recognize these if you can. Here is a equilateral triangle with 90 degrees. That means this must be a 45-45 triangle. So I have been given one side, and I need to solve for side A. In order to be able to get side A of this triangle, I need to be able to connect this measurement to this triangle, and that's going to be done through this side here, which is the opposite side of 60 degrees. So this problem, I'm not going to use the trig ratios. I'm just going to use the similar triangles, because really this is what these special triangles are about. We want to relate it to the similar triangles that we know, the standard triangles here. Okay, and we have to get to know these ratios. So these special triangle problems imply exact values. So we don't want to give any decimal answers for these. So I need to be able to relate this side here. I'm going to call this side x and this side to this side. Okay, so this is going to be my opposite side of 60 to the hypotenuse. And when I look at my special triangle, and I'm just going to draw out my special triangle here. My special triangle is 1, 2, square root 3. Okay, so this side here, x, relates to the root 3 side. So I'm going to do x to 5 is equal to square root 3, and 5 relates to the hypotenuse. Okay, so once I've done that, I can solve for the exact value of x. So I get 5 root 3 over 2. So here we want to solve for a. Now we could use Pythagoras to solve for a, and that will give us exact value. In this case here, I'm just going to relate it to the special triangle though, because we have our special triangle ratios that we're using. And for the 45-degree triangle, it's 1, 1, root 2. And so when I write out the ratio of, this is going to be 5 root 3 over 2. So my ratio is going to be 5 root 3 over 2 compared to length A. And that's going to be equal to the two sides on this triangle that we're going to compare it to. This is going to be my hypotenuse to adjacent side. Okay, so the way I've set it up, this is actually not a trig ratio because hypotenuse and adjacent side. So I'll call this one 45 degrees. The adjacent side to A. Sorry, A is adjacent side to 45 degrees. This is not a trig ratio that we're familiar with. This is adjacent, hypotenuse over adjacent. There is a ratio for this, but these are called reciprocal ratios. We don't get into this right now. So we have this upside down. So I can still solve this ratio, okay? And I can solve this algebraically for A. I'm just going to flip it around. I'm just going to say A adjacent to hypotenuse is equal to 1 to root 2. And this is equal to adjacent to hypotenuse is cosine. So this is going to be cosine of 45 degrees. Okay, and this is just now involving the cosine ratio, which we don't really need to do to solve this problem. So here I'm going to solve this algebraically. So A is equal to, well, I'm going to cross multiply this. So this ends up in the numerator. Now I didn't really need to do this because really in any complex fraction, divide goes on bottom, times goes on top. So this is times root 3, 5 times root 3. That's divide by 2. That's a divide by root 2. So there it is. There's my solution for side A. So side A has a length of 5 root 3 over 2 root 2. And we just leave our answer in that form. Same with this one here. I'm just going to highlight these in red. Okay, we leave our answers in the exact value square root form. Here we have a problem. We have 3 pipes, radius 20 are stacked as follows and determine the height of the stack. So we need to find our special triangle in here, and it should be fairly obvious that it is an equilateral triangle that we're going to deal with. And we're going to then use a 30-60 ratios. And what we've been given is a radius. So this distance here to here is 20. Now, if we try to draw an equilateral triangle along the outside, we do get an equilateral triangle. The problem with this equilateral triangle is we don't know any measurements in this equilateral triangle. Well, that's not going to help us out. So what we need is to generate the equilateral triangle, and generally with these circle problems, this is a strategy you should note. Okay, in these circle problems, we probably should connect our centers. Okay, because the centers connected, we can get measurements of these distances based on the radius, and we know that this is going to be 40, 40, 40 along the bottom, and that's going to give us part of the height. Okay, so that's going to give us the partial height from here to here. The missing heights from here to here is really just the radius here and the radius here. Okay, so that's going to be, I'm just going to write those in, so we know the radius already is 20. So this is going to be 20 and 20. So really the only length that we need to solve for is this length right there. And I'm just going to draw that triangle, the blue triangle over here. It is a 30-60 triangle. And we know that the bottom length here is going to be 20. We know this is 40 and 20. And we're just looking for this length here, which we can add on to get our height. So comparing this to the known triangle, it's going to be that long side is root 3. I'm just going to use these two sides. I'm going to use 1 and root 3. So x to 20 happens to be the sine ratio. It's going to be root 3 to 1. And then solving for this length of x, I get 20 root 3. Okay, so this length works out to be 20 square root 3. We leave it as 20 square root 3. We want to keep the exact values. And then we add this together. 20 root 3 plus 20 is going to be plus 40. Since these are non-like radicals, we just leave them as they are. This is our exact value solution. We don't try to mess with this. Okay, we can work out a decimal value here. Okay, but this is the solution we want in exact values. This is approximately equal to, if I type this into my calculator, I get 20 square root 3 plus 40, and that gives me about 74.64.